All right, thanks so much, Dushan, and thanks everyone for coming. So my project, which I will be talking about today, is about the cultural evolution of cooperation in large language models. Um, and just as a bit of background motivation, so what we're thinking of here is sort of a near future where there are many AI agents that are interacting with one another autonomously on behalf of various individuals and organizations in the world, carrying out various tasks, trading, etc. Could be lots of different things. Um, but many current safety evals are sort of focused on single turn interactions between one model and one human. Um, so we may also want to consider the long-term dynamics of multiple of these agents sort of interacting across generations and changing. Um, and what we do in this project is we look at the cultural evolution of cooperation in a particular setting and find that the sort of level of cooperation that you observe varies substantially between different base models and also between different runs of the same model. So there seems to be this sort of sensitive dependence on initial conditions. Okay, so here's the plan. First, I'll go into a bit of background on cooperation and cultural evolution. I'll then describe the experimental setup we have, which is an indirect reciprocity game where there is cultural transmission of strategies. I'll then go into the results and finally draw out some lessons and next steps and a call to action. So background. So what do I mean by cooperation in this context? There's lots of different definitions in different literatures. One that will be useful for this project defines cooperation as finding an agreement for mutual benefit, even in the face of opportunities for individual gain at the expense of others. So this means that cooperation is something that can't be achieved unilaterally. And as distinct from altruism, which means just to provide something to an individual or group at some personal cost. Of course, in many cases, cooperation sort of can require or build on altruism to get going. So there's altruistic punishment where people pay some costs to punish free riders, but conceptually they're distinct. So one question you might have about all of this is, well, why should we want AI agents to cooperate in the first place? And I imagine that these interactions will take many different forms. In some cases, we say in a market context, we might want more competition. But generally speaking, just like humans can cooperate to achieve outcomes that are to everyone's advantage, so too we should expect that cooperation among these AI agents can enable outcomes that are advantageous for all of the different parties involved. So we can think of matching systems where AI agents represent employers and job seekers, donors and charities, etc., where they could cooperate to create more efficient matching systems. Or it could be something that involves contributing to a public good, such as writing a paper together or reaching climate change agreements, anything of the sort. And in addition, failure of certain forms of AI cooperation could potentially erode some human social norms. So you might imagine that AIs are tasked with buying tickets for events, and they proceed to sort of buy up all the concert or sports tickets only to cancel or resell them later. And of course, just to flag, there are, as I'm sure people will be aware, lots of potential downsides to AI cooperation as well. So AI collusion, or sort of AIs cooperating with one another against humans. But yeah, just flagging that we don't want to indiscriminately promote all forms of AI cooperation. So what mechanisms can support the emergence of cooperation? Lots of this, of course, has been studied in evolutionary game theory and by economists. The most obvious one, of course, is kin selection, where natural selection can favor cooperation between individuals if they are sufficiently related. There's also direct reciprocity, where you help someone and they will help you later. So if you have sort of repeated interactions with a neighbor, you can be fairly confident that if you help them now, maybe they will reciprocate later. And so that's something that can sustain cooperation in that way. Then there's indirect reciprocity, where instead you help someone and then someone else helps you, which is what we'll be focusing on, and I'll say a bit more on the next slide. There's also network reciprocity, where if you can cooperate selectively with those close to you, that can also support cooperation. And multi-level selection or group selection, which some hypothesize has played a big role in sort of the evolution of human cooperation, whereby groups that have more stronger norms of cooperation within the group can outcompete other groups, be it militarily or economically. But so what we've decided to focus on in this sort of first initial study was indirect reciprocity. And like I said, indirect reciprocity is about helping or cooperating with individuals who have helped others rather than those who have directly helped you. For this to work, you need some knowledge of partners' previous behavior, i.e. their reputation. So you don't want to indiscriminately cooperate with strangers, but rather do so selectively with those who have behaved nicely in the past. And this is something that can support cooperation at much larger scales than either, say, kin selection or direct reciprocity, given that typically there won't be that many individuals that you're sufficiently related to for kin selection to work. And with direct reciprocity, there's a limit to the number of people you expect to encounter sufficiently frequently for that to work. And so, yeah, so many think that this has played a significant role in the cultural evolution of human cooperation. So what do I mean by cultural evolution? Not all of you may be familiar with this. So many forms of human cooperation have emerged via this process of cultural evolution. And culture in this sense is defined very broadly as any socially transmitted information that's capable of affecting behavior. And the reason we can talk about culture evolving is that it satisfies these three of Darwin's conditions. So first, there's variation. So there's diversity in ideas, beliefs, behaviors within the population. And there's transmission. These ideas, beliefs, behaviors get passed from one individual to another, or from generation to generation through teaching, imitation, learning, etc. And finally, there's selection. So some ideas, behaviors, practices are, for whatever reason, more likely to be adopted or remembered and spread than others. So when these, oh yeah, here's just a bit of an overview to show you some of the main differences between genetic and cultural evolution. So obviously the sort of thing that gets that is evolving or that gets transmitted is different. So genes versus ideas, behaviors, etc. Genes are primarily inherited vertically, that is from your biological parents, whereas of course cultural items can be inherited from your biological parents, but also from members of your own generation in the case of horizontal transmission, or what's sometimes called oblique transmission, sort of from other members of your parents' generations. And of course, from way back from reading old books or whatever. So the sources of variation are different. Innovation and learn. Oops, sorry, these should be swapped around. Mutation and recombination in the case of genetic evolution. Innovation, learning. It's also copying errors in cultural transmission. And of course, cultural evolution doesn't necessarily concern these discrete units like genetic evolution does. So now we claim that AI agents will be subject to cultural evolution in this sense, and it will happen on many different scales. So you can think of, the various updated base models that different companies release as sort of being subject to cultural evolution. You can also think of, the behavior of individual instances that are interacting with one another as relevant unit. And yeah, so the key thing is that these three conditions will be satisfied. And so the research questions that we decided to focus on for this project was then, to what extent are LLMs capable of indirect reciprocity? And does this enable the cultural evolution of cooperation across generations? And how sensitive is this to the initial composition of the population? So with that, onto the experimental setup that we designed. So we get LLM agents to play this game, which we call the donor game, which is a game that tests for indirect reciprocity. And so there's some number of players, 12 in our sort of canonical simulations, and they're each at the start given an initial endowment of 10 units. Each round they're paired together. One of them is a donor and the other is a recipient. The donor then decides how much of what they have they want to give up, and then the recipient receives 2x that amount, which sort of represents the gains from cooperation. So the average amount that anyone ends up with would be maximized if everyone is always donating everything they have. And so then they alternate between being donors in one round and recipients in the next. And then they play this game for 12 rounds. Before the game starts, they're prompted to generate a strategy that they will follow in the game. So they're given a description of the game and sort of prompted to formulate a strategy. After the game has finished, the top 50% of agents, in terms of how many resources they have, will survive to a subsequent generation. And when the new agents are initialized for the next generation, sort of the other half there, before they formulate their own strategy, they get to see the strategies of the surviving agents and sort of use that as inspiration. So that, of course, represents the cultural transmission step here. And just to put some numbers on this, what are the possible payoffs here? Well, in your sort of best case scenario, if you always defect, but everyone else cooperates maximally, that is, they give away everything they have, you could at most end up with 81,910. Whereas if everyone always defects like you do, then there are no multipliers, so everyone just keeps that they started with. So this is like a real social dilemma where each individual has an incentive to act in their own self-interest. But if everyone does so, it leads to a worse outcome for all participants. So just to show you how it works in a bit more detail. So here's our first generation of 12 agents. Before the game starts, they're prompted to generate the strategy. They then play this donor game. They're paired together, and donors are prompted for how many units do you want to give up. Next round, sort of roles are reversed and pairings switched. They do this for 12 rounds. And then there's selection, where half of the agents, those who had most resources at the end, survive until the next generation. Then there's cultural transmission to the new agents that get added. And so they see these surviving strategies when they formulate their own strategy. These two groups make up the next generation, and they play the game again. Here's just to give you an overview of the information that we're giving these agents. So here are the 4 different prompts we use. So there's the system prompt, which explains the task, the game that they're about to play. Then there's the strategy prompt for the first generation, which basically just uses chain of thought prompting to get them to generate the strategy. And the next generation strategy prompt is the same, except it adds in the survivor strategies. And then when donors get prompted, they get to see what their current resources are, how many resources the recipient has, and how the recipient has previously behaved, which, i.e. the reputation, which I'll get to next. And finally, some chain of thought prompting there as well. So what should we tell them about recipient behavior? This is an example of the type of information they will get. So they're told it's now round 4, you've been paired with this agent. They get to see how much that agent donated in the previous round, and to whom. And then they see who that person was previously paired with and what they did, going back for at most 3 layers like this. Okay, why do we do this? So we thought of these sort of traces as an incomplete summary of the interaction history. So at first we did try giving agents the sort of full history of everything that had gone on and get them to figure out sort of reputation from that, but that turned out not to work. And so we came up with this sort of alternative and thought, okay, 3 layers back seemed sort of within context for humans. Let's start with that and see what we can get. And the sort of further background reason why we do this is that evolutionarily stable strategies that support cooperation in this kind of indirect reciprocity setup depend on higher order information. So when you're interacting with someone, you don't want to know only how generous they've been, but who they've been generous to, because otherwise you risk sort of free riders infiltrating the population if no one is sort of punishing them by not giving them anything. Okay, so on to results. So here we looked at 3 models. So Claude 3.5 Sonnet, Gemini 1.5 Flash, and I should say GPT-4o there. And so what we look at here is for each generation, we look at, okay, what's the average resources that the agents of that generation have at the end of the game. And for each LLM here, this is based on 5 different runs. And as you can see, there are some fairly striking differences here. Obviously, with Claude 3.5 Sonnet outperforming the others, and also being the only one where we see this sort of cultural evolution as the sort of average payoffs increase over time. Okay, so looking at the individual results in a bit more detail, here are the 5 separate runs of Claude. And as you can see, there are a few down here that, not that much seem to be happening, and others where it takes off. And so you see what appears to be the sort of sensitive dependence on the initial conditions of, what were the initial strategies that were present. And here's an example of how these strategies evolve that they come up with. So I've put 2 samples here, one from the first generation and one from the 10th, and tried color coding it a bit so you can see how some parts have evolved. So the first one is start with a moderate donation of 40% in the first round, then in subsequent rounds, donate the average of the recipient's last donation and the 2 preceding donations in the chain, with a minimum donation of 10% and a maximum of 70%. And by the 10th generation, I guess the first thing to note is that sort of complexity has gone up quite a bit. So there's lots of new parameters. Some things look similar, but say the starting donation has now gone up from 40 to 62. It takes a weighted average of the three things it sees in the chain. The sort of high cap has increased from 70% to 89%, and the minimum has also gone up. And then, various further adjustments here. I'll note here also that there's this mention of the final 14% of rounds, but they don't actually know how many rounds there will be. So in effect, this clause in effect never does anything. When you look at the sort of chain of thought output, even when they're at the very end, they still say, oh well, we're not in the final 14% of rounds, so this doesn't matter. Okay, GPT-4o, you'll notice the axis has changed here. So fairly little variation, and of course, very small numbers compared to what Claude achieved. Again, some strategy evolution examples. So here, they start with an initial donation of 20% in the first generation. By generation 10, that's gone down to 6%. And here, as you can see, the sort of complexity has not gone up quite as much, less sort of different numerical parameters. Gemini Flash, similarly somewhere in the middle between these two. And yeah, I'll just quickly mention on the strategy evolution here, interestingly, many of the strategies that Gemini 1.5 Flash generate here don't use any numerical values at all, whereas others do. Just thought, I'm not sure if this is actually very illuminating, but I thought, for one run, each of these models just sort of plot the survival lineages. So here at the top, you see members of the first generation. There's one individual there which survives almost to the end for 9 generations. And the other two look sort of, yeah, like I said, I thought this would be interesting to show. I haven't been able to discern any interesting patterns in this as of yet. So what drives these sort of different behaviors that we observe in these different models? I think probably one big thing is what you see on this graph, the sort of average initial donation size per generation. So looking at the round where they don't have any information about the recipient. Because in some simulations, you get this sort of positive feedback loop where sort of high donations get rewarded. And also thought I just, show the costs per run with these, especially if we want to use something like this as sort of an evaluation scheme. So they vary quite a bit, but nothing of this is like very expensive to run. $10 for Claude, 6-7 for GPT-4o, and 1 cent for 9 cents for Gemini. Another variation we thought we'd try is to introduce the possibility of costly punishment, because it's been seen in sort of lab experiments with human subjects. Introducing costly punishment can be a way of stabilizing cooperation. Of course, in a sense, punishment is already present in what we have, given that you can punish someone by not giving them anything or giving them a very small amount. But we still thought it'd be interesting to see what happens if you explicitly add it in. And here you see again Claude really outperforming the others, and Gemini and GPT-4o looking sort of indistinguishable here. So here's what happens with Claude. I've added the sort of no punishment average here as well. So obviously, I think more runs are needed to verify this, but at least for Claude, it does seem like adding costly punishment does increase cooperative behavior, as you might expect then if you thought LLMs were similar to humans in this regard. But I guess, with GPT-4o, you also see a very moderate increase. But now, of course, it's, from, I don't know, 27 to 37 or so. And Gemini Flash, some reason you see here is sort of adding costly punishment makes cooperative behavior decline quite markedly. And there might be some sort of tipping point phenomenon where if you have enough bias for altruism, that costly punishment can take hold and support good behavior over time in the population, which seems to be the case for Claude, but not for Gemini. And interestingly, when I was running these simulations to get Gemini to work, it sort of first often refused to play when I added this sort of costly punishment option. And I had to go in and change the safety settings to the sort of lowest level in the API. And yeah, I found that interesting because I guess it may be interpreting punishment as something bad or something negative, whereas in this context, obviously, it's something that at least in principle can support cooperation, and also shows how sort of different single agent and multi-agent settings are. So here's just the same slide, but just focused on the actual runs. I think probably no discernible pattern here really. So okay, what are some lessons from this then? So in this sort of very preliminary setup, we see that the cooperative outcomes are very sensitively dependent on initial conditions. Yet many evals today sort of focus on single-turn interactions between AIs and humans to assess safety. And so we think, especially as AIs become more agentic and start getting deployed in the world, that we really need to focus more on sort of new evaluation schemes that focus on the long-term dynamics of multiple LLMs interacting across generations. And like I said, this is only a very preliminary investigation, and there's lots more to study here. So moving on to other selection mechanisms like group selection, also interactions between different models, other types of economic games, and of course more realistic settings as well. But I think there's really nice potential for overlap between lots of work in cultural evolution and LLMs. And indeed, there's probably also room for work in the other direction. So not only using cultural evolution to understand LLMs, but also potentially using LLMs as a tool for modeling human cultural evolution. I don't yet have a preprint, but we will be writing this up as a paper for a conference, hopefully submitting in October. So I'll make sure to share that around then. So yeah, if you're interested in this kind of work, feel very free to get in touch. And so finally, call to action. Yeah, we hope that a new evaluation regime will be developed and adopted by companies and safety organizations interested in assessing sort of longer term societal effects of multi-agent AI interactions. Thanks so much.
Thank you very much, Aron. All right. Again, you can raise your hand if you would like to ask a question with your voice, or you can type it in the Q&A or chat section. All right, Baram, go ahead.
Hey,
and then Richard.
thanks for the oh.
Baram, we cannot hear you. Can you try again? Maybe while Baram fixes Richard, I will allow you to talk. There you go.
Yeah, have you tried different prompting strategies to see if like maybe ChatGPT can be more cooperative?
We have experimented with a bunch of different things, and it was actually fairly hard to get ChatGPT to behave more cooperatively. At one point earlier, we had as an additional source of variation, we gave the agents these big five personalities that they were sort of randomly assigned, or well, either randomly assigned or sort of hand coded. And one thing we noted there is that when I, found some configuration that I guessed would be very favorable to cooperation with Claude that led to almost this sort of like very close to the maximum possible scores, whereas for GPT it had a still notable but much smaller effect. We've also tried working with different sort of priors and saying, well, if you don't know anything about someone, assume that they're generous and sort of err on the side of being too generous. But at least so far, it's been surprisingly hard to get GPT to comparable levels of cooperation.
Thank you.
All right. Baron asks
yes.
question. Let's read it out for
Yes.
audience watching later. Have you looked at whether any of the agents try to free ride? And if not, have you tried introducing free ride?
I have not found any significant free. I mean, not in the sort of strategy evolution. We have looked a bit at seeing what happens when you take agents that their strategies arose from a simulation like this, and then place them in a background population with sort of static strategies. And one thing we tried there was, precisely, what happens if they're in a population where no one donates anything at all. And we did that for a somewhat earlier iteration of this, but there we found, which, as you'd expect, that ChatGPT does do better against a population of sort of free riders than Claude does. So one thing in general to look into more in this is how do these agents do in other scenarios where agents may behave very selfishly or pro-socially. Thanks.
All right. Thank you for the answer. Says Baram. Wojtek asks, not very important, but have you tried rephrasing costly punishment as something that can be seen as more pro-social to avoid the models refusing to play?
No, that's also on our list now, for sure. There were lots of things that we wanted to do, but then initially we had a different reputation system and that didn't quite yield results. So with this new setup where we finally do get some interesting results, at least for Claude, I haven't done as much tinkering as I would like, but I agree that rephrasing costly punishment is high on the list.
Awesome. And Emily Fan asks, I think I may have missed this, but how did you introduce variation mutations in your agents? Like, did you have different linkages for different AIs, and I didn't quite understand it.
Exactly. So so now the only source of variation is basically from the temperature, so from the initial differences in strategies that they come up with. Like I mentioned previously, we had this sort of additional source of variation in the form of big five personalities, but that didn't give the same sort of interesting results where cooperation could increase over time, possibly because I'm not sure, but my hypothesis is that it's got something to do with the fact that differences in personality just overshadowed the sort of gains from cultural evolution.
Yeah, we have two more questions. One from Jonas first. What do you think is optimal in terms of the trade-offs between MARL based experiments on cultural evolution in environments like melting pot or neural MMO versus LLMs based in something like Concordia? Might we not miss important parts if we use pure LLMs?
Yeah, very good question. I don't have a strong view on what is optimal here. I definitely agree that we might miss important parts if we only use pure LLMs. I think we decided to focus on pure LLMs here just as a starting point, and also because there is, of course, some initial research on this sort of social behavior of LLMs, how they behave in various economic games. There was nothing out there that was specifically on indirect reciprocity and how it might evolve culturally. So we thought it would be a good starting point, but it's definitely not meant to imply that we should only focus on pure LLMs.
Makes sense. And Sohaib, I'm sorry if I butchered your name, quite related to the previous question, but did you observe many agents going significantly against their planned strategies? For example, if the overall strategy is very generous, since the survivors get to see them, but the actual actions are defecting.
Not very often. We did see it at times initially, but then we added sort of chain of thought prompting for the donor decision. And so there, they do sort of go through, okay, what information do I have about this person I'm paired with? What's my strategy? How do they fit together? And that seems to have removed sort of mismatch between behavior and strategy.
Awesome. Let me see if there are more questions. Jonas says, thank you. I didn't mean that wasn't worthwhile. I guess my point was more on variation and complexity being easier to encode in RL style environments. If we look towards safety in the future, that might be important.
Yep, yeah, I agree with that.
While there's a lull in the questions coming in, question from me. Are you more concerned in AI to AI interactions kind of spiraling out of control or human and AI interactions going forward?
Good question. I don't have a strong view, but one interesting thing here, which I did mention, is that of course, cultural evolution in AI systems will also impact cultural evolution among humans, and so we shouldn't just focus on the multi-agent, multi-AI dynamics, but also look at what happens when we sort of include humans in the model, of course.
Sounds like future research.
Yes.
Awesome. Yeah, really interesting talk and really interesting like approach to this whole discipline. Yeah, I don't see new questions coming up. I'll give a few seconds for anyone to raise their hands if they want to ask more questions. All right, seems like we are done with questions. Thank you once again, Aron, for the presentation, and
Thank you.